Hey, this is Dr. Sweeney, and this is the fourth part of our exam 2 review. This part is on the central limit theorem and the sampling distribution for the mean. And once you understand how to work with the normal distribution, this is just really like a kind of an application of the normal distribution. It ends up being really important for working with confidence intervals and also with hypothesis testing. But for our purposes, we basically want to know, some very basic ways to shift a traditional normal distribution uh, and some of the requirements for the sampling distribution. So that's pretty much what I'm gonna focus on. One, what is the central limit theorem? Okay. Two, how does it change the applications for the normal distribution? Okay. So let's take a look. And this one here, this is number 13 from the review. And it states the shoe sizes for NBA players are normally distributed with a mean of 15.4 and a standard deviation of 1.7. And then it asks us to use this information to answer the following questions. Right? So notice we got shoe sizes. They're normally distributed. Okay. And we have an average, a mean of 15.4 and a standard deviation of 1.7. So far, so good. Okay. So what that tells me is that the population is normal, right? So the population is normal. And I have these two pieces of information. And that's actually really important. And it's going to be important for using the central limit theorem too. So first, A asks us, have the requirements for the central limit theorem been met? And explain that completely. Well, there are two possible requirements. There's not actually two requirements. We have to have one of two, okay? One is we have to have either the population is normal, okay? Or two, we can have the sample size is greater than or equal to 30. So what that means is this. If we know the population is normal, which is what in this case we do, the shoe size for NBA players is normally distributed. So all I have to say is, well, the shoe sizes for NBA players are normally distributed, so the requirements for the central limit theorem have been met. Okay? Or we know that the sample size n will be greater than 30, greater than or equal to 30. So if I know that that's the case, well then I also know that the central limit theorem conditions have been met. I only need one of these. Notice the or. So I only need one of them. Okay? Consequently, if you know the population is normally distributed, you're done. If you know, on the other hand, the sample size is greater than or equal to 30, you're done. Just mention one of them. Okay? Now, B. Suppose that we wanted to create a sampling distribution for the mean shoe size for samples of size n equals 42. Would the sampling distribution be approximately normal? Okay? And then it asks us, would the mean and standard deviation of the sampling distribution be? Okay? And then we want to show all of our work. Well, these are the requirements for the central limit theorem. Okay? And then these are the results. We call them the results of the theorem. Okay? One is the sampling distribution is approximately normal. The sampling distribution is approximately normal because we have met the requirements. Okay? So the sampling distribution is approximately normal. That's the first result. The second result is that mu of x bar, which is the mean for our sampling distribution, is equal to mu, which in this case, oh, well, that's not so bad. That's 15.4. Okay? And then three, this one is the important one that's actually really different. This changes everything about what you're doing for the sampling distributions. It's going to be sigma of x bar is going to equal sigma over the square root of n. Okay? So sigma, in this case, is 1.7. And notice n equals 42. So we get 1.7 divided by the square root of 42. Okay? and that's equal to 0.262. Now, something to notice here about that, that's way smaller than 1.7. So one of the things that happens when we generate a sampling distribution for the mean is we're actually asking about like the probability of getting averages of a particular size. So since we're looking for the probability of averages of a particular size, their standard deviation is a lot smaller because it's harder to get further away from the mean. I talked about that inside of the actual lesson as we increase our sample size, our spread gets smaller and smaller because we're taking the square root, we're dividing by the square root of the sample size. So notice that. These are the results, right? This is the big change right here. That standard deviation ends up changing as a result of the central limit theorem. So anytime you're generating a sampling distribution, you need to use, right, this sigma of x bar, okay? Now, what is the probability that an individual NBA player would have a shoe size greater than size 14? Find the z-score, write an appropriate notation, and construct a graph. Then write the answer. One of the things that you want to notice is that this question is a lot like the one that we just did for the normal distribution. In fact, it's identical, okay? And there's a reason why I highlighted individual NBA player. It's because we are not going to use the central limit theorem or the sampling distribution for this question. Sampling distributions are for samples and for averages, okay? This is an individual, and it's out of a population. So we're going to have, I'll write my mu equals 15.4. And remember what I said that big difference is? Sigma here now is 1.7, right? Because we're looking for the individual NBA player. Okay? So, and then our x here is going to be equal to 14. So, our z-score, will equal 15.4 minus 14 divided by 1.7, which will equal 0.824. Okay? Now, I'm going to draw my distribution. Oh, by the way, I should write my notation, huh? Probability that x will be greater than 14. Really important too, because notice it's a greater than sign. So I have, here's 15.4. 0.824, that's right about here. It's a little bit less than 1 standard deviation away from the mean. So there's 14. X equals 14. And then here's the value. Then we just go ahead and we'll shade it out. There it is. Done. Ta-da! Okay. Now, I'm going to go in. I'm going to go Stat Crunch. I'm going to put in my mean and my standard deviation. So 15.4 is my mean. My standard deviation is 1.7. And I want to know the probability that x is, in fact, greater than or equal to 14. I compute. And there it is, 0.795. Makes sense to me. Looks about right too, right? Okay, that looks, it's quite a bit more than 50%, right? It's almost 80% of the entire distribution. Okay? All right, cool. Now, let's take a look at this. This actually ends up being D. This is C. This is D. Okay. What is the probability that a sample of size 42 would have a mean of between 15.5 and 17.5? All right. Well, first, one thing that I first want you to notice: it's a sample of size 42, and we're looking for the probability of a mean existing versus individual NBA player. You guys get that? So now what we're looking at is if I pick 42 players at random, what's the probability that one out of those 42 players, what is the probability that the average foot size for those 42 players is going to be between 15.5 and 17.5? Okay? Now, Now that I've identified that I'm looking at sampling distribution for the mean, right? Okay, sample, mean, right? I now have mu is going to be 17, or excuse me, it's 15.4, just like it was before, right? Because mu of x bar equals mu of x, equals mu. Then sigma of x bar, right? We found it for size 42 already. Right, sigma of x bar is going to be this value here, right? The 1.7 over root 42. So that's 0.262. 262 was 262. Yeah. 262. We're looking for the probability that x is between 15.5 and 17.5. Okay. And so now I need to find my z-scores. So the z-score for 15.5 is going to be 15.5 minus 15.4 divided by 0.262. Right? That's going to be very different than if we utilized 1.7. I promise you that. .382. Then we'll take the z-score for 17.5. Now, you're thinking to yourself, you know what? It's only like 2.1, so it shouldn't be that big. But we're going to go through it and divide it through by 0.262. Wow. That's going to end up being really far away from that's going to equal 8.015. So it's 8.015 standard deviations away from the mean. It's like a ridiculously far distance away from the mean. So we've got here's 15.4. We're going to start out about halfway, like a little less than half a standard deviation away. So there's 15.5. Notice that even though it's only 0.1, it's pretty far away. Okay? So it's 0.382 standard deviations away. And then 17.5 is I mean, like, you know, it's out here. Here's 17.5. It's so far out. It's not even like on the range when we use the empirical rule. Okay, so it's way out there. So we're not even, I mean, like, we barely even have to worry about it. So let's just go in here. We'll now draw our picture, or bubble it in. So anytime you have a standard like a z-score that's bigger than, oh, I don't know, 4, or really 3, it ends up, it's so far away that it barely adds anything to the overall area, right? It's basically the equivalent of if we said, okay, go all the way out to the end. Okay, so there's that. There's our picture. And now we'll go in, take 15.4. Now, notice something. If I had kept it at 1.7, watch this. Okay, take 15.5 to 17.5. Look at that picture. First things first, remember how I said 17.5 was like way over, it's 8 standard deviations away from the mean? It isn't anymore. With a standard deviation of 1.7, it's not even 2 standard deviations away from the mean. Okay, it's like 1.5. So, wow, that's going to be really far off. But when I go in, oh, and sorry, let me just actually show one more thing. It's going to be 0.368, right? That's the probability there. Let's just do a comparison now to when we have 0.262 as my probability, as my standard deviation. Oh, wow. Now what you're looking at is it's way farther over, and we're actually bubbling in the entirety of the like the end of the distribution, the whole tail of that distribution, and our probability now is 0.351, mostly because we've actually dropped off a big chunk of the middle part. So 0.351. Okay, get how different those pictures are, right? 0.351. Okay, cool. All right, so what do you need to know, or what are some of the most important things that you need to know to work with the central limit theorem and sampling distributions for the mean? Well, the first is that we're going to utilize the central limit theorem, and so you need to know those requirements. Those requirements are, one, the population is normal, or the sample size is greater than or equal to 30. Then we know what the results are. The results then are the sampling distribution is approximately normal, the mean of the distribution is the same as the mean for the population, and the standard deviation is going to equal the standard deviation for the population divided by the square root of n. So as n gets bigger, our standard deviation ends up getting smaller. That's going to come in really important when we do confidence intervals. As n gets bigger, the standard deviation ends up getting smaller. Okay? Now, when we are doing problems or applications using the central limit theorem, here's the big difference. One, they're going to run basically the same way as you would work with the normal distribution ones. Like E, the next one here, is just like the last one I did for the normal. Okay? What we need to do is we need to make sure that we are identifying when we're going to use the population values or when we are going to use the central limit theorem values, the ones from the sampling distribution for the mean. How do we know? The ones for the population are going to be individuals, and the ones for the sampling distributions are going to be samples, and we're looking for averages. Okay, so that's going to differentiate the two. Once we've differentiated whether or not we're going to use the sampling distribution or the population one, right, with the individuals, then it's a matter of writing down your mean and standard deviation or your mean and standard deviation for the sampling distribution. Okay, don't forget, go in and practice. This is something to study. This is something that you got to know from study, okay? And same with the requirements for this central limit theorem, okay? All right, I hope that helps.